Okay, guys, so right now we're going to talk about the kinetic molecular theory of gases made up of 4 parts. The first part is that all matter is made of particles in motion except at absolute zero. The second part is collisions between particles are perfectly elastic. The third part, average energy of particles is directly related to temperature, and gas particles have a negligible volume. Okay, so we're going to talk about each one of those. So let's go over the first one first. All matter is made of particles that are in constant motion. So even in solids, solids are still vibrating in place. Okay, so they're vibrating in place. Liquids, they slide past one another. And gases, we say that gases have no intermolecular forces. Okay, we know this isn't really true, but um, that's what we say. Okay, so gases are free to move and they have no intermolecular forces. Okay, at absolute zero, that's the only time when we have no molecular motion. Theoretically, we cannot get to absolute zero, but scientists have gotten pretty close. Next, two, collisions between particles are perfectly elastic. Elastic means that they don't lose energy. Okay, they're not losing energy. The energy might be transferred to another object, but the amount of energy that goes into a collision and leaves the collision is the same. So particles can speed up or slow down, but how much energy they lose is how much another particle gains. Okay, there's no loss or gain of energy. Okay, so it can be transferred from one particle to another, but it's no loss or gain. Okay. Next part. The average energy of the particles is directly related to temperature. And this, we're always talking about the Kelvin temperature. Okay, we wanna make sure we're looking at Kelvin temperature. Okay, when we're comparing temperatures, we want to look at Kelvin. Okay, one of the tricks they always like to tell us is like they'll give you something like, what happens if we go from 1 degree or that's a bad example, 100 degrees Celsius to 500 degrees Celsius, right? Well, it's not really a 5 times the amount of energy. It's because this is 373. This is 8. This is, sorry, 773. It's not 5 times. Okay, yeah, 100 to 500 is 5 times, but if you add 273 to both of these, it changes the 5 times. It's no longer 5 times. It's really like twice as much. Okay, so make sure you pay attention to Kelvin temperature when you're comparing kinetic energy, okay? Also, the next thing we got to look at here, you should know this name, this Maxwell-Boltzmann distribution curve. You should know this, okay? Know the name and know what it is, okay? What it does is it shows the distribution of particles at different temperatures. So part B here says that not all particles have the same kinetic energy. Okay, the overall average kinetic energy is related to temperature, but even when you have something that's very, very hot, you'll have some particles that are moving very slow. So you see the red here, some of these particles are moving very slow. Okay, whereas most of the particles are moving fast. And even at low temperatures, even when you have something that's cold, there are still some particles that are moving very fast. Okay. The Maxwell-Boltzmann distribution curve, it actually helps us to describe why things evaporate. Okay? Because even at low temperatures, so even if you have something at a low temperature, so let's call this green like a relatively low temperature, there's still some particles in this green part that have a lot of energy. Okay, so if this was the amount of energy, if this line represented the amount of energy needed to escape to the gas phase, so if that represented how much energy needs to go to the gas phase, you see that some particles have enough energy to go to the gas phase. Okay, even the blue, this line kind of extends out. There's still some that can go to the gas phase. Okay, and that's what happens with evaporation. Okay, now there's also something known as evaporative cooling. So evaporative cooling. So what happens is as these high energy particles, as they leave to go to the gas phase, right? Let's say we have a liquid and some of these go to the gas. We're losing the highest energy particles. We lose high energy particles, which therefore lowers the average kinetic energy or the temperature. Okay, so as the high energy particles leave, the temperature actually gets lower. Okay, that's what we call evaporative cooling. Okay. Next thing, let's talk about root mean squared velocity. So root mean squared velocity measures the velocities of particles at a given time. So some particles may move slow, others move quick, okay? But they're all constantly moving. The velocity, even for some of them, could equal 0, okay? To properly assess the average velocity, we use average of the squares of the velocities, and that's known as the root mean squared velocity. Okay, with this is the formula right down here. Okay, the velocity is given in meters per second. Be careful though, because the R value that they use here is 8.314. It's not that 0.0821 that we usually use. It's 8.314. The temperature has to be in Kelvin, and the molecular mass is actually in kilograms per mole. So this is also it's kilograms per mole. So if you're ever asked to do a problem with root mean squared velocity, just keep in mind that the R value is 8.314 and that the molecular mass is in kilograms per mole instead of grams per mole. So essentially you're just taking the molar mass over 1,000, just dividing it by 1,000. Okay. Last one. Gas particles have a negligible volume. So we assume that the size of the gas particles don't occupy any space. I know it's kind of it's not really true, but we just assume that they don't occupy any space. Okay. Now let's talk about the difference between ideal versus real. So ideal gas and real gas are different, right? Ideally, we just say ideal to it makes it easier to deal with. All right, it's just easier to deal with. So ideal gases, individual particles do not have any volume. They do not attract or repel one another, and they collide elastically. Okay. However, in reality, real gases, they do have discernible volume. They do attract and repel each other slightly, and they do sometimes collide inelastically. Really, some of the energy goes into heat or light, or it's transferred to the container, right? So it's not perfect. Now, ideal gases behave least ideally at high pressures and low temperatures. That's because the particles are closest together and they're moving the slowest. So the more they interact with one another, the less ideally they behave, right? Because if you remember, they do not have volume, but if they move slowly, you start to see the volume. And then also, if they do not retract or repel each other, if they're moving really slowly again, they're closer to each other, so they interact with each other more. Okay. So if you look at the graph here, ideal and real gases are very similar at high temperatures and actually low pressures. It should be kind of the opposite way here. This should be actually, I think this graph is wrong. But as you increase the pressure and decrease the temperature, then they behave. Yeah, this graph should be like this. And it should be more like this, because at high pressures and low temperatures, yeah, high temperatures, low pressures, they should be the most ideal. Yeah, I don't know. I don't even know how you draw this. Draw it like this, probably. And then ideal would be least and best. It'll just get better as temperature goes up, pressure goes down, then they behave most ideally. And as temperature goes down, pressure goes up. Actually, it should be like flipped around, yeah. Anyway, don't look at this. This is a confusing graph. Just know high pressure, low temperature, least ideal. Yeah. And then low pressure, high temperature, most ideal. I don't like that graph. No one this graph's ugly. Doesn't make sense. Okay, you're gonna see it probably better here. Oh, that's why, because they have, yeah. So as pressure goes up, you'll see it ideal gas compared to the other gases there. Low pressures, yeah. Anyway, so that's that. Go away. Okay, so this is just a little statement here. I'm not going to read it, but you can pause the thing and read it if you like. Okay, and that's all I have to say about kinetic molecular theory for right now. Hopefully that all makes sense to y'all.